So we are still continuing with the concept of normal distribution and standardized normal distribution curve. And we've had a big formula later on that we've seen. And the formula we've been using to standardize the curve. You guys, I think you remember, it was z is equal to x minus mu over the sigma, which sigma we say is the standard deviation. Sigma is the standard deviation of the population. So this is what we had earlier on. Now we want to apply this concept of the normal distribution curve into a z. If we were given a z-test, how would we apply it? This would become z is equal to x minus x bar over s. So here we are dealing with a sample. This one is for the population. If you're to remember all the content we've been seeing, this is for the population, because this is mean of the population, standard deviation of the population. So if we need the ones for the sample, this will be mean of the sample, and as well S will be the standard deviation of the sample. So in our calculations, when we are dealing with a z-test, one sample, so let me introduce a term called one sample z-test. In a one sample z-test, we'll be utilizing this formula. And in this one sample z-test, the population has to be of n greater than 30. But we want to further see something interesting about a z-test. A z-test has what we call z-values or z-critical values. They are the ones we are going to apply here. Let's first have this at the back of our minds as we proceed with this. So we are saying the thing is simply normal, standardized normal distribution. So we have our curve there. Then we have the curve. We obtain the curve here, and it's a normal distribution curve. We imagine our n is greater than 30. So we have what we call criticals of z criticals, and the criticals, we have two criticals. We have a critical at 95 and a critical at 99. So a critical at 95% and a critical at 99%. So a critical at 95% is the one for the probability p is equal to 0.05. And a critical of 99% is the one for p for a probability of equaling to 0.01. So at 99%, an event has a probability of 0.01. We give it a probability of 0.01. And at 95, we give it a probability of 0.05. So we have standard criticals for z values. At 95, let's say this is p is equal to 0.05. At 95, we'll have a critical, a z critical value of 1.96. So the curve is asymmetrical. We'll as well have the same value this side, but a negative value. So this side it will be negative 1.96. Now this is also p is equal to 0.05. So that is a critical, a standard critical for a z value of p is equal to 0.05. So we can, this is a 95% region, or we can simply call it 0.95. We can define it in terms of numbers, 0.95. Because if we have 95 over 100, you will get the 0.95. Simply that. So if we get a value, inside this region, inside, let's say we calculate a z value, and I get my z calculated when it is less than z-cal less than the z critical, the z critical. In other words, my z-cal is less than 1.96, and I get, that means the value is inside the curve because it is less. Imagine we have something like 0.1. So it will be inside the curve. So if I get this, I will accept the null hypothesis. Accept the null hypothesis. We are going to have a deeper look at what the null means, at what the null hypothesis means. But this is a point I wanted us to have currently. If this at the z critical values at 95 or probability of 0.05, we have 1.96. And if we get a value less than the critical, we accept the null. If we get a value greater than the critical, the z critical, we reject the null hypothesis. The null hypothesis. Why? So there is something also we need to digest before we go further with this test. If we have the same curve, just the same curve, the probability is somewhere there, and the probability is also somewhere here. And we get a value inside the critical, where we say it's the acceptance region, where we accept the null from. So getting an event inside here means we have no statistical significance. So we can also define a value inside here as being not statistically significant. Why? Because it has a greater probability of happening. And if we are to also define in terms of probability, getting a value inside here, in terms of probability, it will be P, our probability will be P is greater than 0.05. Because we said inside here we have 0.95. So there are higher chances, it's greater for an event to be randomly selected among these ones. So the probability is greater than the 0.05. If we get a value outside the acceptance region, like when it's in the rejection region, we'll define in terms of probability as P being less than 0.05. And in terms of statistical significance, getting a value outside the acceptance region, that means that we'll get something which is statistically significant. So we'll have a high degree of statistical significance because there are less chances of such an event happening. But again, we are going to combine a probability of 0.05 and a probability of 0.09 on the same graph, and we try to interpret, we try to summarize the concepts, the concept of defining the probability and the statistical significance. So we'll have a graph combining both. So a curve, the curve is, so if this is our curve, and so I want us to combine both probabilities on the same curve, and we see. So this is P is equal to 0.05. Then we say the critical for Z is 1.96. What we do on the right side, we as well do it on the left side. So this will be negative 1.96. And this will be P is equal to 0.05. But we can as well have the one for negatives, for the 99% confidence, P is equal to 0.01. And the critical for this is 2.58. We do the same. Actually, this is a negative. So this will be 2.58, the critical, and this is P is equal to 0.01. So this is 95% confidence at 95%. This is at 99%. So whenever they ask you 95, you do at P is equal to 0.05. Then whenever they ask you 99, you do at P, you calculate at P is equal to 0.01. So that is what we have there. So in terms of probability, if you get your answer a z value that is equal, a z value that is equal to 1.96, a z value, z equaling to 1.96, like the value here. That means your probability P is equal to 0.05. If you get a z value, a z value, a z value less than the critical. So if we have our z value less than, no, this is greater, less than, a z value less than critical, less than the critical, in other words, less than 1.96 at a probability of 95, we'll say that P is greater. The P will be greater than 0.05. So if we get a value in the acceptance region, P is greater than 0.05. So if we get a z value, our calculated z value, less than z value, in fact, sorry for this, if we had a z value less than, sorry, this is less, yeah, it was, yeah, surely it is right, it was less, z value less than the critical, we say P is greater than 0.05, that is fine. So if we have a z value greater, a z value, if the z value we've calculated is greater than the critical, or greater than 1.96, this 1.96, we say that P is less than 0.05. So here we'll say this is statistically non-significant, and here we'll say that this is statistically significant. That is at 95%. So we're going to see the same thing at 99%. The variation is just a little variation happens, but the concept remains the same. So at 99%, still we are dealing with the same thing. Probability, if we get a z value, calculated z value, equivalent to 2.58, we'll say that the probability is equivalent to 0.01. But if we get the z calculated, like this side, being less than the critical, that is less than 2.58, less than 2.58, we'll say that P is greater than 0.01, and this is, in statistically significant terms, it is not statistically significant. Then if just we get the z-cal greater than 2.58, that means we'll define our P being P less than 0.01, and this will be statistically, here we have a little variation, very significant, statistically very significant. Why am I adding the word very significant? Because we are doing this at a confidence of 99% rather than not a confidence of 95. So if you're 95% confident and someone is 99% confidence, their confidence at 99 is way higher than the one for 95. That's why we say it is statistically very significant. So this is how we can apply the concept, and this is very important when we need to understand this as we are going to do our conclusions when doing the z-test and the t-test and other tests of how to play around with the probability and other things. Thank you for